you cannot calculate the error for that. But you can calculate the uncertainty, and the uncertainty is the possible ranges of the errors that will come tomorrow.
So let's try to break down the concept of uncertainties into some distinct categories. So we have the irreducible uncertainties, data uncertainties, uncertainties in measurements, in the model, and also in the parameters of the model. So let's look a bit more into detail of these ones. So the irreducible uncertainty is a type of uncertainty in your underlying process that you're trying to model that is sort of inherent in the system that cannot be removed. It's not your fault, so to say. A sort of clean example would be quantum mechanics. Say you have a spin of an electron and you measure it in another, you have it known to be in, say, along the z-axis, and then you measure it along a different direction, deviating by some angle theta. Then the probability of getting spin up versus compared to spin down is given by some pure random, pure probability, depending on this parameter. So in some systems, there are really inherent uncertainty. We have data uncertainty.
Yes. So what we mean by data uncertainty, basically, we divide up in 3 different categories. So the first one is the local resolution, right? And that is, so given your data set, let's say that we have a data set A. So how well is it resolved in this space A? So if it's resolved very well, then we have less uncertainty between the different data points in the set A that we have. And the second one is, are we covering the full space? Are all the possible ranges of our variables? So let's say that there's some others, like our variable can also be captured in the B space. Then, of course, our data is only like observing A, not observing B. So if we go outside of A, and our model never saw that before, of course, it will be uncertain. And then there's another one. So which explanatory variables that you put into your model are you putting into the right ones? So, for example, if you want to predict the electrical load in Stockholm, and you only do that with the temperature, is that enough to explain the full problem? And we'll actually see an example of this later.
Next, measurement uncertainty is, I think, very clear. You sample data, and there will always be some sensor noise in your signal. That's an important consideration as well. Then model uncertainty is maybe one of the more interesting ones. Yeah. So it's important that the model we use to approximate the underlying system. We want it ideally to be a universal function approximation, that it can approximate any behavior of the underlying system. But this we can never reach in practice. So what we use is some sort of approximation to this. Neural networks are a typical example of this. And we reduce the model uncertainty by making the model more complex in some ways, so that it can handle more varieties of functions. So in the case of neural networks, well, we vary the layers and the number of neurons in each layer. So we are increasing the complexity and thereby making the neural network, which is a type of function approximator, we make it more powerful. Another more like clean example is the simple Taylor phantoms. So clearly, the more terms you use, the better it can approximate functions. So also a drawback is if you just increase the model complexity, it will in general increase, it will decrease the model uncertainty, but it will increase the parameter uncertainty. And what we mean by parameter uncertainty is, well,
is this. So what we mean by parameter uncertainty, we have, let's keep on this example with neural network. So we have some neural network and we have some parameters in the weights and the biases. And do we have the best set of parameters given our model? So we don't care about if our model is the best model for a specific problem, or even if it's the right model. It's just, is it the best given the model? And I don't, yeah, exactly. It's not. And then we can reduce the weight, like the loss function, with updating the weights in the neural network. But then, when do we know if we'll like reach a local optima or like global optima? So for some methods that are complex, like linear regression or other methods, and you know that you will find the best parameters, and then your parameters are going to be basically zero. You know the parameters. But in other cases, it's not like that. And then overfitting can be seen as a consequence, or like a combination of both the data and the parameters. Okay, so this framework of thinking about uncertainty is actually quite interesting because it can also map to your like machine learning problem in a more general sense. So you have all these different questions in a machine learning problem. Should I can I prove the model results? Should I like collect more data? Should I like completely change the model to another model? A bigger model, more complex model? And all these questions, if you know the uncertainty split that you have, like you can divide up all the uncertainties that you have. You know, like, okay, my model is performing bad because of data uncertainty. But then I need to collect more data. And not the other way around. It seems like to me, like many of the machine learning problems, people are just randomly like doing any of these actions to improve the model. So they're not really doing it in a structured manner. So, and that's of course a very hard task to calculate all this uncertainty. But theoretically, if you could do that, it would be really helpful.
And there are some different approaches to doing this that try to solve different aspects of characterizing uncertainty. I mean, for example, the measurement uncertainty is not the type of uncertainty that is relevant really when you're building your model. It's of course your data pipeline. But we're going to look into Bayesian neural networks, mixed density networks, also using dropout as a base Bayesian approximation.
I mean, that's like a fallacy that people use. They say like, okay, I have my image classifier, and I classify this image with 95% probability. And then they think that they are certain about if it's actually the right image that they classify. But softmax as output is not a measure of uncertainty. And that's a misconception in many machine learning projects that it's in.
So perhaps the main goal for people being interested in probabilistic machine learning is that they want to, in one way or another, capture the uncertainty of the output of it. And that is one approach. The Bayesian neural networks don't really do that. They rather focus on capturing the uncertainty in the parameter quantity. And not long ago, we had a great talk by Carl, where he discussed Bayesian neural networks in more detail. I'm not going to do that here, but more give you the intuition about it. So on this side here, we have just a standard neural network, and the flow of information is to pass in the input, and what propagates through the feed-forward process is just some numbers, really. When we have Bayesian neural networks, we model the weights by probability distribution. And so what you get out in the end is essentially information. Say that you're very uncertain about one of the weights. That information will sort of propagate through the network out to the input as well, to the output. And it will, I mean, this is more of a way of characterizing the uncertainty in the weights, in the inner workings of the network, rather than characterizing the uncertainties in the output. But this is, I mean, there's really some overlap here, because if you have uncertainties in the weights, that of course indicates that you're uncertain about your output. So we had a discussion about that during the presentation that we of how much can be used for this purpose and not, and it's not completely clear. And it's you can give examples of where it performs badly. We're going to see some examples later. That's down to the mixed density network.
Yeah, and like in a nutshell, the mixed density network is having the uncertainty on the top of the neural network. So instead of like having uncertainty of all weights, you predict in the output data instead of predicting like one value. This is my truth. This is my prediction. We predict a mixture of solving parametric probability distribution and normal distribution, for example. So then in that case, it would be to predict the weights, the means, and the standard deviations. And then you combine these, and then you get a new probability.
So you can think of it, say, if you have an ordinary neural network with, say, k outputs, if you want to convert that, so to say, into a mixture density network, so you assume you model your outputs as Gaussians, and then each of your outputs becomes 3 outputs: the mean, the standard deviation, and then the weight. And then you sum these Gaussians together, and then you get a mixture model. So that's why you call it mixture density.
And one interesting thing here is actually that just as like the basic linear neural networks are universal function approximators, these guys are universal probability distribution approximators. So theoretically, they can predict any probability distribution. So it's a nice fact. You don't rely on some parametric distribution that you want to predict, and then you are something wrong.
I already want to hint to the fact that sure, the network learns in some way the variance of the output, but this must be learned. So you still need to see lots of data and then learn the variance. And then we have dropout as a way of sort of probing the uncertainties, which is a really interesting approach that's very performant because you just use a normal neural network. During the feed-forward process, you remove some of the neurons, and you pass in your input and get out an output, which is of course going to be different because you're not using all the weights, not all the parameters of the network are being used. So say you do this 100 times for the same input, but you use different dropout each time, and then you can sort of look at the variance of the output in that case, and that turns out to be a good measure of the uncertainty. We give some references to papers that show the proof for this work. So one way to more like intuitively think about this, what's going on, if we go from a deterministic or standard neural network or model that outputs just a number versus a probabilistic case. So in the case of a model outputting just a number, we get the loss as the squared error, for example. But how should we think about it if the output is a probability distribution? Well, then the loss is really just how much wrong is your output probability distribution compared to the true one. And there's the feedback-Lieber divergence, which measures sort of the difference between probability distributions. When we look into that, maybe we should not. I mean, are we giving you time to ask questions? Is it going ahead? Yes. Sure.
So, is it like you measure the ratio and the standard deviation and so on over the pictures and the weights, when you look at the weights over time? Oh, okay, this situation.
Right.
Do you care about open up for that? The only thing is how do you just care about fund situation?
Yeah, so similar to standard neural network, you initialize your weights in some way. In exactly the same way here, you need to initialize the probability distribution for each weight. And I guess the standard way of doing that is assigning them to some Gaussians with random variance. And then the training, the backpropagation algorithm becomes quite different. I don't know the details, maybe Carl can fill you in later. But
it's differentiable with respect to the parameters of the distribution. So I think it's quite similar if I'm not.
Basically, you can argue that it's still the same. You're increasing the complexity of the model. So, for instance, if you model each parameter, each weight to be Gaussian, then you like kind of scale up the complexity by a factor of 2. But it could be arbitrary by any distribution.
You don't have a problem that they are interacting. The mean understanding is good. They are not independent. So it's your distribution. I mean, when you are training, you are doing the best of it.
Yeah, okay, so usually what you do, you can do it a different way, but usually what you do is that you kind of like want to approximate the theories, which is very intractable to solve analytically. So basically what you do is that you make a parametric approximation, kind of like the same way as you do with function approximation. Kind of like think about it as you want to fit the best sine wave, the best second order polynomial. Usually what you do is that you take like a multivariate Gaussian where each weight is independent of each other. That's an easy word with. You're not claiming that this is the true position. This is the best fit.
Okay. So the way this is done, the way to think about it is what we call variational inference. And so really what we want to do is approximate to gain information about the true probability distribution of the data. That can be, in fact, is very difficult. I mean, this is essentially base root, and the denominator is typically the problem here. So what one does in practice is that we approximate the true distribution with some other distribution that we have more control over, which is parameterized by some parameters. And then the problem is essentially reduced to finding the optimal values for the optimal value for this parameter v, which is then the minimal, the v that results in the minimal scale divergence between the probability distributions. And this scale divergence can be thought of as a metric or distance between probability distributions, but it's not symmetric, so it's not a true metric. You can think of it as measuring sort of the relative entropy between the distributions. So in practice, there are many inference methods, and we're going to have a look at the Edward library, which is a package for doing probabilistic machine learning related to tensorflow.
Yeah, so that was enough for the theory, I guess.
I think so, yes. We're going to go into some more code examples and some demos.
Cool. Right. Okay, yeah, so we built some notebooks using Edward as a set, and they're all up on the GitHub, so I can send that in the
we'll paste links to the code and to the slides after.
So first of all, we talked about inverse problems, and that was actually the first use of mixed density networks that Christopher Bishop, he was the one publishing in '94, I think. How these networks could be set up and how it could be used. And the toy problem he had was inverse problems. And we actually have an example of this in Edward. So this is basically its I think it could work. So this is basically the data set that I use. We've created some data set that is not a function, of course, because it has multiple y values for every x value. And then, so if we would try to fit our neural network to that function, then we fail miserably, as you can see in this picture here. So it tries to kind of predict the mean, and the mean doesn't have to like point to mean. If it's between two modes of your distribution, then it doesn't even like no data points can be there. So instead, you want to predict like a distribution or a probability distribution over this inverse problem. And first, yeah, of course, like splitting it up into like testing and training samples. And here is where the whole thing starts. So it's just as simple. For all of you that use Keras and TensorFlow, it's just as simple using Edward. So basically, what you do is you just define your model. So yeah, it's just a vanilla dense neural network. And then in the end, so this is the difference, like Victor said before, is that in the end of this having one output, then we will have k times 3 outputs, k weights, k mu's, and k sigmas. And in this case, I think I put k to be 10 here. So that means that we have 30 outputs, predicting all the whole parameterization of our probabilities. And then you, yeah.
Since they're Gaussian, we're essentially predicting possibly 10 different modes. Exactly. But as we saw, at most we had at most, I think, 4 or 5.
So exactly. So you see here, maybe here you have a lot of modes. So 1, 2, 3, 4, 5 even. Yeah. So the thing is that you need to have at least as many mixtures components as the number of modes in the distribution. Otherwise, you cannot predict it, right? And that's hard if you don't know the data. But, the more components you add, the more it can predict. And you can always turn off components or try to. Theoretically, that's what Bishop argues, is that if a component is not needed, then we just put the weights to be 0 for the component, and then that's turned off. Yes.
Is there a way to know if it's not happening?
I mean, there will be part of the data that your model never
Yeah.
predicts.
So if you can visualize it and see that you don't have enough components, or if you can like try to increase the number of components, and then you see that your loss function is still going down, maybe something like that, and then until some point it stops going down, and then you know, okay, I have enough. So the thing here is that okay, the output activation for the mu's, since it's a regression problem, it's linear. For the sigmas, we put like exponential, but it could also be a soft twist. We don't want it to be negative, right? Because it's a standard. It's a variance, yeah. And then the weights that we want to be like a convex set. So we want them to sum up to 1, and want every one of them to be between 0 and 1. And then to do that, we pass it into a function or a cast in Edward called categorical, and that makes sure that we do that criteria. And then in the inferences, it's as simple as this, like when it comes to implementation. So you specify like Edward.map, like maximum posterior inference. And then the whole of your inference and all the gradients and all your loss functions, everything is set up for you. So that's pre-implemented. So it's very simple use. And then, yeah, you do your inference here. Nothing that wrong. You can look at the graph, you see that the loss function is converging. So this is the log likelihood that we want to maximize. And then when we predict, you can see here, for example, here's one of the predictions that we have. And the true x value here is somewhere like 0.37. And we predicted it to be 0.8. And the true value was around 0.8, and we predicted all these distributions. So if you would go back and look at the value at here somewhere, we have like 1, 2, 3, maybe 4 modes. That was what we predicted. We predicted all these 4 modes.
And it's quite clear that the last one here, much faster. It's what these 2 modes merge together.
Okay, so and let's use other samples. You can also, when you have a probabilistic problem, you can also sample from it. So that's another nice feature. So you can actually just run, or in this case, you have a like conditional probabilistic problem. So given your x, you can sample from it. So that's what we do here. And we can see that the data that we sample is quite similar to the data that we had in the beginning, except for here. And then you could wonder, like, why is it off here? And why is it off here as well? And then if you would plot all the news, all the means that you have in your mixed density network, then this corresponds to these 10 components. And you see that the news, they are following like straight lines and capturing different parts of the data. And what you want to have, of course, since our data set is going like this, what you want to have is that from here onwards, outside of the data set, you will have 0 weight on these news. So the brightness of these circles is proportional to the size of the weight. And you see that these are quite bright, actually. So it's not doing a perfect job, and I'm not sure why. When I looked and you did the same example with instead of having normal distributions, that had beta distributions, then you got something like this instead. So it was actually doing quite better here, which was interesting, I think. And it didn't go completely straight, so it's kind of turned somewhere. Anyway, so what did you say? The distribution. So now it's a mixture of betas. Before it was a mixture of deltas.
And what priority is? What priority?
I mean, so in the mixed density case, you don't have a. You don't have an explicit prior, right? So you just have your mixed density network.
We assume it to be of a certain distribution, and you initialize the parameters on that. So you start out with some prior in that sense.
Yeah. So here, as you said here. So here you specify the components. So that could be seen as a priorities. And in this case, it's all of them are beta. I don't even know. Maybe you could mix components. You have one Gaussian and one beta. Anyway, okay. So here is another example that we will do quite quick. And this is actually relates to what we talked about before. So that was the first with the inverse problem. This relates to the noise level of your neural network. So how well can you predict? So we had uncertainty of the measurement uncertainty, where we said like, okay, if there's noise in the data, then we cannot predict as well, right? So there's some irreducible error if we have noise. And I used we made some a stupid example of sine wave that we will get sick of today, it's I made 4 of them with different variances on the noise. So 0.1 standard deviation, 0.2, 0.3, and no noise. And then you see that this is splitting up the data as we did before. Here is actually training. So here is the one without noise. So here is zero loss. So you see that actually loss function goes all the way down to 0 after some number of iterations. And so we completely captured the phenomena that we have. So we were able to fit this sine wave very well. But of course, outside the domain where we don't have any data, as we said, we have some uncertainty because we never saw data from that.
But here you're not talking.
No, exactly.
This is the mean of the
Yeah,
output.
this is the mean of the output. 200, but of course it depends on the whatever parameter size and layers. And then when we go up in noise, so now we have standard deviation of 0.1, and then we see. Then I actually plotted here the black line. I plotted the variance or the variance of given standard deviation 0.1. So since this is the mean square error, it represents the variance, the global variance of your prediction. And you see that it actually converges not to 0 anymore, it's hard to see, but to this black line. And going up in the prediction, going up in variance, you see that it's also following the same pattern. That's quite interesting to see. So if you have more noise, then you will have a larger loss function that is irreducible. You cannot do anything about it. And here I just plotted all the the sine waves that we made against the data, and you can see that if you plot the loss against the real sine, so now it's not against the data that you created with the noise, but against the real sine. You see this without any noise, and then the error increases, seems to increase exponentially as you increase noise. So if you know a way to reduce noise in your data, you should definitely do that. I don't know what's interesting to show.
Did we have any plots showing the predicted uncertainty?
Yeah. So let's do that. So we can also use the we talked about using mixed density networks to produce distributions for inverse problems, but we didn't talk about how to use it to predict uncertainties. And that's also something that we can do. Here we have the same data set, like the sine wave again, and now instead of picking a normal here, instead of picking a normal network, here we use the same mixed density network that we talked about before. And what happens? Well, we can train it, we convert this to some value, and then we can try to look at the distribution of this. Okay, here I actually think that I used, let's run this one. It doesn't seem to want to run, but anyway, we started. Yeah. Yeah, are you using CPU machine? Okay, now it comes. Okay, so we have the same data set, we split that into test and fail. You can skip the part of the network. Don't take the network. What you see before, we're using normal components. And then we can train it using network. Now it's training. So yes, we're using maximum multi-story posterior approximation, and I don't know that much about the inferences. We didn't have time to do that much, except how it works. The priors, that's a little bit the same question that we had before. I guess is how you set up the network, right? If you have what are the priors? Yeah. So okay, so here you can see that we have, for example, so that's like an implicit way of setting the priors, right? Because even if you're not patient, you are in some sense. So here we say that we're not patient. We don't have any any weights around or any distributions around our weights, but we use like some random initialization fields. So you have a prior, you know, I don't know. And here is the it's lost curve seems to converge well.
Index the velocity when you break the list of problems.
Yeah.
Goes up.
Here.
So you're using the previous the previous network, and then you just add like whatever you don't use on the last part, which is the mixture.
Exactly. Yeah.
But you could also have a distribution of each weight. Yes.
Yeah. Yeah. No, that's not that. So that's what we talked about before. You could combine like a Bayesian neural network with a mixed density network, right? And then maybe you can actually characterize better your parameter uncertainty as well as the uncertainty in the output. So, and that is not clear to me how that fits together. But it's an interesting research question, I guess. Or do you have any ideas on that?
No, I think it would be interesting to try it out.
Yeah.
I don't know beforehand.
You sample can predict sample.
Yeah, exactly. Yeah, exactly. So that, did I do that? You know what? Let's do that. I think we can. So let's reinitialize the network. Sliced somehow. So if you would sample from so we sample from the mixed density network, and here is the blue points are our training or test data. Remember, this is test data. And then the red points are the samples before we train in our network or the mixed density network. So you can see that our samples are popping up in the whole range of our real data, and that's a good thing, right? So because even to the theory, like setting priors, that's like it's not really. You will, given that you have a probability of non-zero probability of your prior for the right parameters, it will converge if you add on more data. It will converge if you add on more data. So it's not like a really crucial decision, but at least you have to have some probability. If you have a good prior, it might converge faster. And then, of course, now we need to retrain it since we go away all the weights.
So this is based off constant variance in the input.
Yes.
As a first
Yeah,
example
exactly. And then we talked about when we looked into the uncertainty. One thing that comes up is this thing about homoscedasticity and heteroscedasticity. It took me like 2 days to learn how to say those words. And that thing is actually something that we'll show right now, and that's something that will relate to how we use dropout as an uncertainty measure later on. So take a look at this. So now we have homoscedasticity because the variance in the data is the same
independent of x.
Independent of x, exactly. What happens? Well, we train the model, it converges as before. And if we plot the uncertainty, yeah, we get something like this.
I think this is really great showing. Okay. So it's the blue line is the mean, and then each shaded area is the one.
Yeah, it was
quantized of.
Yeah, it was quantized. It's quantized with tens percent.
Right. Okay. Yes. We see that it captures the uncertainty. Looks like. We have some perspective. If you look at the ends, this is a big issue. To say the network predicts that it's quite certain. So this is a clear example of the uncertainty in the prediction must be learned from given data. That's just because this type of model doesn't take into account that if it hasn't seen any data, then it should be uncertain about the prediction. On the other end, looks like depends on where we cut it, I think. But here it seems to increase. But this is sort of random. What happens in the ends?
Exactly.
Sort of mostly depends on the initial weights and how the interactions happen at the border.
And on this slide, this shows, yeah.
No, okay, so the noise level in the input data was 0.2 standard deviation. And then the plotted line here is the predicted standard deviation. So we see that on average it sort of captures the right characteristics, but it's fluctuating quite a bit. Perhaps that will go away if we train it further and have a more complex model. Now let's look at the case of probabilistic data. So the noise varies with the input, with the extra. We see here, initially there's essentially no noise, and then linearly it increases up to, I don't know how much, 0.2.
0.2.
Yeah, 0.2. So then we train the same type of network and see if it learns to predict the varying noise level. The loss is going down.
What is running?
Yeah. I don't know, behind you know.
In the cloud, somewhere in the cloud.
Somewhere in the cloud.
Two cores. So,
I mean, we're not running many iterations. We're training for like half a minute. We have a clean data set. That we've chosen this data set because it's very simple and it captures the relevant characteristics. So now we're plotting prediction for the quantize. Takes a while. The works.
Yeah, actually, I realized when I did this that there's no like analytical way to calculate the quantize from a mixed resolution. So you need to do it like numerical. Correct me if I'm wrong, because then I won't know.
Yeah, so we see that it looks like the predicted uncertainty is growing. The data. It's a bit difficult to see because they have sort of the same color. But we can go to the next plot. Oops. Yeah, we corrected quickly. Yeah, so the dashed black line is the true noise level in the data, and the blue one is the predicted one. And you see that it learns the inherent noise in the data quite well, actually. Which is great.
Yeah, that's quite good.
Yeah.
And that's something that is hard for other methods.
For sure. Should we?
Yeah, this is actually here. Or maybe we can.
Should we take?
We can take this one.
So now, remember we discussed. So we looked at this mixed density network. Now we're going to look at the way of using dropout, having just standard neural network where you sort of run it multiple times in the same input, using different dropouts each time. You still feed forward, and then in the resulting predictions, you can measure then the variance and the mean of those predictions. And let's now look at how.
This is not our work. This is a guy that's a PhD that did a PhD in uncertainty in deep learning called Yarin Gao. You can go in. This is available on his GitHub, and he also has actual PhD available. This is the case when you, as Victor said, when you drop out. And
so maybe should we say scroll up? Yeah, it's running 100 passes with random dropouts. I don't know the probability of the dropout in this case. And so the average of 100 runs is plotted in the dark blue line. And so right now it's training, it's learning, and we see that it converges to the data point, that one, and it predicts.
And the problem here, right, is that it's homoscedastic. Right. So what happens is that here it's a small uncertainty, but here it's much bigger. but the network cannot see that because given good points,
Is this right then?
I think it converges after a while, and then it
Probabilisticity, I guess, means a measure of the.
no, it is only
How much?
It's only the combinated fault. But I think it converges. I'm not. I mean, to be honest, this is not my work. I don't know exactly how he calculated the bands here, because these are run by Monte Carlo simulations, right? In your network, so you don't really get the bands. You only get a lot of different predictions. So how he did this, I'm not sure. But the point here is that he only has one single thing in the output, and that is the prediction. He doesn't have a probability distribution. So what if? So here, for example, here it seems to be at least almost as if you would add like a point here and a point here, shouldn't be able to do both of those. No,
That's a good example.
That's me.
Is it?
Just to explain what the dropout is.
Yeah. I think you had a slide on it. We can go back to the slide.
Yeah. That's a good point so that everyone follows.
Yeah.
So, if say we have a trained neural network, and we pass in some input and do the feed forward to get our output. We are using all the weights are being used to calculate the output. Say now that, as opposed to this, I disable, so I invalidate some neurons, no data will pass through these ones. So essentially I have a smaller neural network from the one I started with. And then I pass in the input and do the feed forward. I will get some output. Next time, so this is what we call dropout. This neuron is not good. Next time I do this for the same input, I will do the dropout for some other neurons will be dropped out. And the dropout is done by just, with probability, say 10%, a neuron will be disabled. Do this, say 100 times. You're doing different dropouts each time. You get different 100 different outputs. And then you, from these 100 outputs from the same input, you can calculate the variance. Assuming that they're Gaussian, I mean, you could try to approximate the probability distribution of Gaussian. Let's assume it is. That's what's done in the demo. Does that make it more clear what's going on? Otherwise, please ask a question.
But he did also, this guy, young guy, he did another one with elasticity. Yeah, so here he's supposedly has some elasticity, so it's not only predicting one value. I mean, it's also predicting the standard deviation for every X value, for every input value.
So maybe like add lots of data points at some part and do that. And then later here, let's add lots of data.
Like
just lots of them at the same point, so that you have a big loss of not going there. Yeah, something like this. Now I think we will need. Yeah, we'll see. So since we have lots of data points here, the network will be kind of sure that this is the right prediction. You see that the variance is small. And here, well, yes, see what's going on. So it turns out that this method is apparently quite effective at modeling the uncertainty in the data. And the very nice thing with using dropout in this way is it's not more expensive in the training or anything like this. It is a standard neural network. The training, just as usual. Well, the penalty here is that you need to do the feed forward, the prediction, in this case 100 times for each.
So that means that every network that you ever trained in the past that has dropout in it, you can use it as a to provide uncertainty bands. but you can only use it for homoscedastic uncertainty. You don't also change a bit of the output. Because here in this case, change a bit of the output. You also have a standard deviation in that. And then you need to retrain it, of course. I think I have like a really quick example with dropout, and also like the same sine wave.
Yes, this is interesting. Yeah. Because one thing that one really would like to have from a model like this is that gives an estimate of the uncertainty in the prediction. It's important then for this model to, I mean, it's interesting to ask how does it perform when it hasn't seen data in the region before. But as we saw, it can learn from data, it can learn the uncertainty. What happens when there's no data at all in the region?
Here I actually do the same thing as you suggested. So just doing the predictions before you train the network and see, okay, are we in the range of our data? Training the network. Yeah. Then here, yeah, this is something similar to what Jan and Jan did, but this is a harassing implementation of that. And here I used to run, I think, 100 Monte Carlo samples, and you get some spread of the different predictions, but it doesn't seem to capture everything.
And if you're annoyed by this, like piecewise linearity in the output, I guess that's simply because of the comparatively low complexity in the method.
Yeah, and the values.
Yeah, and the linear.
And here it's with the absence of data in the middle. You can actually see here that yeah, it is more certain at this point than at this point. So that's a good thing.
But it doesn't always look this way. Showed me a picture.
It did. I mean, it didn't look. It looked a little bit worse, I think, and it was a bit narrower, but it was still bigger than here. But here it might be small. I don't know. The next step, I guess, here is like, okay, how do you say we're satisfied with this probability distribution? And that you can do if you're working with sine waves, because we can compare it. But I guess you're not always working with sine waves. So to see what is the right probability distribution of the data set of that set. For the last sample, Anton asked me to have some data that is actually domain specific, not only sine waves. So this is for you, Anton. As I said, I work with a company called Probibalistic with the data science for the power industry. So applications to how you use energy in a smarter way. And this specific example is I use the data set. I use the data from the transmission system operator in Sweden called SVK. They measure how much electricity we use with our projectors and whatnot in Stockholm at every hour. And then also I use the API of SMHI to get the temperatures of in Luna, so it's not exactly here. Close enough. And this is the data. So here is the electricity load, and here is the temperature. Of course, it's not the same units, but it's plotted on the same graph. And you can see that it's more or less a sine wave. And here is the temperature, which is also, I mean, you can see that it's clearly there's some relationship between the temperature and the electricity. And that's of course because of like electric heaters and heat pumps and here's the distributions and all that. And here I put it in a scatter plot. So you see that there's like a negative correlation. So if you have higher temperature, then you have less heat demand from the electricity, which makes sense. And then now the question is, okay, I want to make a regression on that. So should I use like a simple line here? This is the regression. That's why I'm completely confident this is the load in the tomorrow given this temperature. Probably not. And of course, I mean, this is, we also talked about explanatory uncertainty. So now I assume that my whole data set here depends only on temperature, which is completely false. So that's also why I have so much spread. So if I could make some more smart decisions of the explanatory variables that I want to encapsulate in my data, then I might bring down this. Anyway, yeah, some distributions of the data. This is actually quite interesting. So this is like the plot is maybe hard to see, but it's on the legend there is a different month going from January to December, and you can see that actually in different month here you are on different parts of it. So going from January to December, you see that this is everyone is in the same state. So all of the sum of all these plots make the plots we saw before. So you can see that in the winter month we are kind of in the upper left corner. So here is winter, here is also winter, and then in the summer month here, like June, July, August, we're in the bottom right. Yeah.
This one plot corresponds to 1 day.
1 hour. Sorry. 1 hour. Yeah, 1 hour.
Also, I guess that the lots of fluctuation here are coming from different
Yeah, sure.
daytime, nighttime.
Yeah. So leaving up, testing train data again, and then plotting our predictions for our mixed dust network without any training. See that we are our prior is in the same range, and then training it, and then plot it again, and then we say okay. Now we have something that might be more sensible than only having like a single line regression. I wouldn't sell this, but but it's better than having a line regression. And then we can also do the sampling, and we see that when we sample from our model, it's kind of similar to the data that we have. So we're satisfied. I think that's it. I think.
So just to sum up, maybe using probabilistic methods and quantifying your uncertainties is something that I guess everyone is interested in some way. We are using essentially black box cases, and it's very important. I mean, one step to be closer to have an understanding of the output would be to have an understanding of the uncertainty in the prediction, and the applications are very wide and very many fields. And I myself working with financial data, portfolio data, and we try to make predictions and estimates for risk metrics, etc. This is super interesting for us as well. But afterwards, we'd love to hear your thoughts about this and where you would like to implement similar methods. And that's it. So questions? Yes.
After are we going to post these notebooks? Where are we going to post them?
We're going to post them in the Facebook.
Yeah, in the Facebook group.
Is there here?
Publicly accessible for non-Facebook people.
Do you have an idea? Do you hear?
I mean, I guess we're going to post it.
I mean, it's on my GitHub. It's already online, so you can check out. My nick is Sebaheg.
I guess we're going to place it on. We can post it on AI.
We can post it on the website. So after the talk,
let's say like this on AI Week. Let's see where we have all the events. Right under this event, we're going to post the link.
Yeah. Perfect.
Okay. Yes.
One of the criticisms really nice. One of the criticisms against probabilistic machine learning in general is how it's called with finding high dimensions. Have you guys looked into like generating like performance to take samples in high dimensions?
So we at Analytics, we are like starting up. We're going probabilistic. So we're trying to take the step of being like only deterministic or point forecasting, doing probabilistic forecasting, because that's where you can actually use as input to make optimal decisions. We have not tried this on our production models, and so I have not to if this works. I will probably run into a bunch of problems.
Which models will you start with? what do you think is most fun, given what you know so far?
So actually, we didn't talk. I started looking into this like mixed density network because I thought that okay, Bayesian neural networks, they are too computational and intensive. That's what everyone is saying. They won't scale and so on. And then we start thinking about okay, but maybe this like dropouts, that could be nice because then we only need to put them to dropouts. Then we can have like some fusions of our uncertainty. But turns out that yeah, it's homoscedastic, and probably our data is not homoscedastic. So that was the reason for going to mixed density networks. But then, after doing that, I met with some experts in the field, and they said, "Don't waste your time with mixed density networks." I talked to some guys from the university, for example, and they seen that in the image recognition domain that you were trying to set up like image recognition or detection problems, like regression problems, and that worked, kind of. But then, when they set it up as a classification problem, it worked much better. So that, I think, is the next step for us to look into. How can we actually make this a probabilistic, like probabilistic regression, using framing it as a classification problem?
How does it affect the training?
So I wrote a blog post on that, I think, on mixed density networks and on the flow program. And I think actually in the implementation of that work, I think they used to solve it like don't do X or whatever. So I don't know, just like some set of like transformations that you solve, transform your data to avoid the on the flow problem. X no, thank you. Min max.
That's a way of avoiding underflows when taking products.
Yeah.
How is this thing that you're showing? They actually help us solve the group. Yeah.
What's that?
It's type of regression because it's type of like
Okay.
a lot of noise and variance data.
Yeah.
It actually uses a classic calculus.
Cool. Thanks for that. Thanks. Yeah.
What are the weights? I mean, when I take the science curve, what would be the weights?
So the weights in the neural network, in the weights in the network, you mean?
Yeah, I mean, would it be like one would have
Is that what you mean?
yeah, I mean, for the simple problem.
Yeah.
So sorry for the sine wave. I didn't say that, but for the sine wave, usually you don't know what your distribution is, right? So you don't know how many mixture components you should have. But for the sine wave, it's single model, so it's unimodal, and we only have one Gaussian. So actually, I only use one component here. So the weight of that component is obviously one, right?
Yeah.
But in the other problem, when you have an inverse problem, then we have 10 components, and then the weights are given by the intensity of the surface here.
You would have, but if you would have 2 or 3 components, the sine state then it would be like
Yeah.
one would be 1 and the other 2 would be 0. It would be sort of
Good question. Yeah. I don't know if they would like split up evenly or if they would turn off 2 of them and just keep the other one.
I guess it wouldn't really matter. The prediction would be the same. So I don't. As I understand it, the network wouldn't favor any of them really. It would sort of depend on the initial parameter where it ends up, because they are equally good in some.
Yeah.
If you take 2 of them that are equally two modes that are equally good, or just one of them, and they look the same. As far as I see it.
and the weight would be just 1 over how many components.
I guess, I mean, you could do some regularization on this, for having some L1 regularization, trying to have as few modes as possible.
Yeah.
That would be quite good.
Okay, say that you have, in this case, so you would do the prediction, have 3 components. You do the combination, you combine them. they basically get 3 different.
Yeah, we didn't write that down, but it's a sum of.
Maybe here you can see different examples of. So yeah, it's a sum of the different components.
Say that the output were for each output you have the weights alpha 1, mu1, sigma 1, and for the other one alpha 2, etc. And then the total output is then the alpha 1 times a Gaussian with the parameters mu1, sigma 1, plus alpha 2 times the Gaussian with mu2 and sigma 2 parameters. That's it. With that,
Yeah.
which is, I mean, if you plot that resulting this probability distribution, it will look like.
Thank you.
Thanks.
I'll just say a few things. Thank you everyone for coming. Thank you, Birger, for making it very possible. Thanks, speakers. So I heard there's a really nice talk tomorrow as well at the castle in Airy. And finally, I think it's like sunny outside. It's good. So I was thinking if you want to join and go down to this nice park and just chill and talk about AI, I'm going to do that. Someone do it?
Sounds good.
Everyone come.